Hello, I'm Quentin Gemin from Blacklight Analytics, and I'm going to present a joint work with Sébastien Mathieu and Damien Ernst from the University of Liège. This work is about short-term active distribution network operation under uncertainty and associated decision-making problem. So, let's first summarize what motivated this work. A significant challenge for electrical distribution systems is to successfully integrate more and more renewable energy generation in the network. This causes major technical issues, and it is not realistic to solve these problems by only upgrading the grid infrastructure, mainly because of the cost. An alternative approach is to connect distributed generators under non-firm access contracts. By doing so, generators can, for example, produce at the maximum capacity as long as the electrical grid can support it, but they may also need to reduce their production level in case of congestion or voltage issues. So, distribution system operators have the ability to impose dynamic access limits to these generators, and they can do so as allowed by the regulation, which can be defined at the local, regional, or national level. In this work, we first formalize how to compute dynamic access limits under a stochastic framework, and we then present a resolution procedure for the formulated decision-making problem. The formulation accounts for the constraints that must be respected to ensure the proper operation of the network, for the delays that may affect the transmission or the application of the access limits, and for the rules imposed by the regulation. The resolution procedure is valid for radial distribution network, which is how most distribution networks are operated, and for regulations that impose a last-in, first-out order for curtailing generators. The decision timeline of the problem can be divided into 3 time periods of length delta t, which can typically range from 5 to 15 minutes. At every time step t, there is first a decision period during which the distribution system operator can perform forecast and any other required computation to determine the relevant access limits. It is then followed by a communication period, at the beginning of which the computed access limits must be transmitted to the generators. These generators then have a hold time period to implement the transmitted limits, which become effective at the operation period. So, because of the computation and communication delays, the access limit determined at step t only come into effect 2 time periods later. Now that the timeline has been presented, we are going to ignore time subscript for the sake of simplicity and focus on designing a small model of the distribution system to supervise. The set of constrained assets in the distribution network is denoted by a set A, and each asset of this set has a power limit PMAPS, over which the power PA flowing in the asset cannot go. In this illustrative distribution network, if we for example consider that the transformers A1 and A2 have a power limit, as well as the lines or cables A3, 4, and 5, the set of constrained assets will consist of these 5 elements. We then denote by G the set of generators with dynamic access limit, and overline P as the set of access limits that apply to all these generators. Assuming that every generator G in the figure has a non-firm access contract, the set of generators with dynamic access limit will contain generators 1 to 5. We can now introduce a stochastic problem as the following optimization problem. In this problem, we want to minimize the expected power curtailment, or, in other words, to determine the least restrictive access limits. And we want to do so while ensuring that the congestion risk is low enough. The probability that the power flow in a constrained asset will be higher than its power limit Pmax must then be lower than some constant Ra, which corresponds to the risk tolerance of the distribution system operator. Every access limit must of course respect technical limits of the corresponding generator, and, finally, the limits must be compatible with the regulatory framework. We choose to denote by Z the set of all access limit solutions which fulfill regulatory rules. The stochastic formulation has now been defined, and we are going to explore a compatible resolution procedure. We first need to model how the power injection at generators and at other sources influence the power flowing through constrained assets. At every decision step T, the procedure starts by interpreting the radial topology of the distribution network, and by converting it into a directed acyclic graph. Every internal node N of this graph is a set of constrained assets AN. And so, considering the same example as before, we would need to create 3 nodes of constrained assets to match the topology of the network, and to connect them, again, as defined by the topology. Then, each leaf node S of this directed acyclic graph corresponds to a power source. A power source is either a load or a generator connected to the network, and therefore influences the power flows in the grid. In the example, the 5 curtailable generators are a subset of the sources, and connect to internal nodes of assets as indicated by the lines, cables, and transformers in the topology. We also choose to represent network loads by a single source under every internal node. Each of these loads models all the consumption processes under the corresponding constrained assets. We can now express the power Pn flowing in an internal node as the sum of the power injected by its downstream sources Dn as defined by the directed acyclic graph. In the example, the power flowing through A2 is the sum of the power injected or consumed by generator G4 and G5 and by load L2. The node A1 being at the top of the graph, its power flow is the sum of all the sources. It is important to note that, given the timeline of a decision problem, all the introduced power variables are actually random variables, and their actual value is not known with certainty at the decision step. The resolution procedure thus relies on forecast to estimate the relevant access limits for the operation period, which is 2 time periods ahead of the decision step. These forecasts are computed from historical measurements of the power injected at every source, and consist in a multivariate Gaussian distribution of the multivariate random variable of the power injection of sources. In other words, we compute a probabilistic forecast that is a Gaussian distribution over a random vector, of which each dimension is the random variable of the power injected by a leaf node of the directed acyclic graph that models the distribution systems. The forecasting process works as follows. First, we have access to the historical time series of the power injected by sources up to the decision period T, and over a time range of at least several hours. These time series serve as a dataset for per-source Gaussian process regressions, leading to uncorrelated mean and variance estimates of the 2 time periods ahead power injection of every source, and to a covariance estimation step that approximates how every power source correlates with the others. Using the output of the per-source forecast, the covariance matrix is then scaled to match the variances of the uncorrelated forecasts. At the end of the process, we recover the mean vector and the covariance matrix that define the 2 time periods ahead probabilistic forecast of the random vector of the power injection at sources. Now that probabilistic forecasts are available, we need to assess the congestion risk of constrained assets. The power Pn flowing through asset of an internal node AN of the graph is the sum of the random variable of its downstream sources in Dn. However, we do not have a straightforward analytical density function for this sum, and instead of finding a complex and density-dependent closed-form expression, we choose to represent the distribution of Pn as a set of samples. This is done by first sampling from the multivariate Gaussian distribution of sources, which accounts for the correlation between power injections, and then by performing a sample-wise sum of the sampled vectors, but limited to the dimensions corresponding to the downstream sources of An. By working on samples instead of analytical density functions, we can account for the effect of an access limit on a generator by just clipping all sampled values that are over this limit. It is also simple to evaluate the congestion risk of an asset, as it is equal to the share of samples at this asset that exceed the power limit Pmax. Let's illustrate this concept with two examples. This figure shows the density function of the power forecast of a generator, including the effect of its access limit, as indicated by the clipped part of the Gaussian at the right. Summing such distributions leads to density functions such as, for example, this second figure. The right and left parts of a density function results, among other things, from the access limits and technical limits at the cross-label generators. Now that we can evaluate the congestion risk for every constrained asset, we can define an algorithm for computing the optimal access limits. Let Z LIFO denote the last in first out order imposed by the regulation, and let overline PG be the set of all access limits but the one of generator G. The access limits computation procedure can be summarized as follows. First, initialize the access limit of every generator to its technical maximum. Start modulating the last in generator according to the regulation Z LIFO, and determine the access limit to impose to this generator such that the congestion risk of every asset is mitigated. If it is not possible to mitigate all congestion risk by curtailing this generator, set its limit to its technical minimum, and repeat the procedure for the next generator according to Z LIFO until the congestion risk at every asset is below the risk tolerance. A test system and quantitative results can be found in the paper, but I will here present SADO, a software solution which relies on the presented problem and resolution procedure to compute preventive access limits for distribution generators. You can see a schematic representation of a simple distribution network with a single distribution substation as electrical node, to which two constrained assets are connected. By clicking on one of the assets, you can see that its power limit is 12 MW. The blue line indicates the evolution of the power flow in this asset over time. This power flow is influenced by the power injected by these two generators, which are wind farms with an installed capacity of 18 MW each. By clicking on one of these generators, we can see both the evolution of the power production over time in blue and the probabilistic forecast in green, where the light green area represents the 99.5% confidence interval of the probabilistic forecast. If we look at the confidence interval of the power flow forecast at a constrained asset, we can see that it exceeds the power limit at two places. This means that, without taking any action, the congestion risk is not acceptable at these moments. By looking at the wind production chart, we can see that the algorithm computed access limits as indicated in red at the corresponding moments. If the increase in power production had reached higher level, the asset would not have been congested thanks to the transmitted production limits. To conclude, we formalized the operational problem faced by a DSO in setting short-term access limits under uncertainty. who provided a resolution method for this problem, which is compatible with radial distribution networks. The method relies on clipped multivariate Gaussian sampling to compute probabilistic forecast of the work flowing in constrained assets. And finally, by relying on samples instead of analytical density functions, we were able to easily account for the effect of access limits of generators and to evaluate the congestion risk of assets efficiently.